two forces, F1 and F2, magnitude 35 and 50 respectively, act on the same box suspended above the ground. F1 is 55 degrees, F2 is 35 with a horizontal, as shown in the diagram below. Excellent. Define term equilibrium. Nope, don't know what that is. Draw a closed vector diagram, triangle forces for the above. Nope, don't even know what that means. Calculate the mass of the block. All right, let's do this. So I'm going to say, we'll draw a free body diagram. So the free body diagram is F1, F2, and then we have force gravity pulling it down. I think that's it. So what I'm going to do then is, I'm not going to, this isn't drawing a more of a free body diagram. This is decomposing vectors. So this is going to be F2. This is going to be F2x. This is going to be F2y. Switch over to orange, not because we need it, but because it is convenient to show change in thought process. F1x, F1y. So I'm basically breaking it up into x and y components. That way we can look at these vectors independently. We can look at the x direction independently of the y direction. So we're going to do SOHCAHTOA. That's supposed to be in S. I'm going to start with 2. So we're going to start with cosine. So cosine of theta, we'll call this theta 2, equals adjacent over hypotenuse, which is F2. Actually, I hope I should write that up. You're correct. Good call. Adjacent over hypotenuse. Adjacent is F2x, and hypotenuse is just going to be F2. Long story short, when we then rearrange this, we get F2x equals, let's see, F2x, move that over there, F2 times cosine of theta 2. Putting that into a calculator, we'll do F2, which we know is, actually I should write this over here. So this one is 35, this one is 50. So we're going to do 50 times cosine of 35 degrees. And I'm going to do some rounding here just because it's convenient. So I'm going to call this one 40.96. So this will be 40.96 for F2x. Actually, I'm going to leave it that way for now. So this is going to be 40.96. We do something similar. We find F2y is going to be F2 sine of theta 2. And then when we apply the same concept over with F1, we're going to find that F1y is going to be F1 sine of theta 1, and F2x is going to be F1 cosine of theta 1. And I went through that second part kind of quick. It's good if you can to go through the whole SOHCAHTOA thing just to make sure you get the angles correct. All right, so now that we've decomposed vectors, we're going to look at Newton's second law. Newton's second law is the idea that sum of all forces equals 0. So I'm going to start by looking at the y direction. Sum of all forces in the y direction is going to equal, and I'm going to say that's F1y plus F2y minus force gravity equals 0. Now, really, it's plus force gravity, but I said minus force gravity because it's going to be a negative value. And so if I say that force gravity is positive, I can just take the negative and move it out. I like to be positive in life, and so that's why I like to deal with positive numbers in subtraction instead of the implied negative value. Long story short, these are up, these are down. By these, I mean this one specific gravity. And then we're going to expand this a little bit. So this is F1 sine theta 1 plus F2 sine of theta 2, because that's F1y, F2y, equals force gravity. Force gravity is going to equal mass times gravity. So if we want to find the mass, all we do for this one is we take gravity, move it over. So it's going to be F1 sine of theta 1. You're right. I'm going to cheat and just copy and paste. Not fair, but it is convenient. Often cheating is convenient. All right. So I'm going to put some numbers in this. So F1 we know is 35. 35 times sine of 55, specifically 55 degrees, plus 55 sine of 35, also degrees, divided by gravity, which I'm going to say is 9.8. So now we're going to put that all into an equation. So 35 times sine of 55 degrees plus 55 times sine of 35 degrees divided by gravity, 9.8. I could say 9.81, doesn't matter. And we get a mass of 6.14 kilograms. So the force going down is going to be 6.14 kilograms. And we didn't really need to use the X components. If we were trying to find like the tension in the wires, we'd probably have to find F1, F2, we'd probably have to do that. We could, not a big deal. But that's how we'd find the mass using the sum of all forces in the Y direction. All right, part D, by part D I mean 2.4. What will be the net force acting on the box if F2 is removed? Okay, so for this one, I'm going to draw a picture. So we have F2, F1, and mass gravity. I am just going to remove F2 and then calculate the resulting forces here. So we know what so what we're going to do then is we're basically going to draw a triangle. So there's not going to be any reorientating of the strings or anything. Just instantaneously, F2 disappears. Which way do things accelerate? Which way does it move? And intuitively, you're going to be like, oh, probably that way. And so we're going to look at it in two parts. We're going to have a force in the X direction and a force in the Y direction. So the force in the X direction is going to be the sum of all forces in the X direction, which in this case is only going to be F1x. And that's going to be, as we found up here, that's supposed to be a 1, F1 cosine theta 1 equals F1 cosine theta 1. Because the other horizontal force, that's from F2, is now gone, and gravity doesn't have any horizontal force, it's only vertical. So that's going to be our X force that we have up here, X force. And then Fy is going to be the sum of all forces in the Y direction, which is going to be mass gravity minus F1 sine of theta, because we know we decided that F1 sine of theta is the Y component right up here of F1. And I had mg positive, meaning that down, the direction of mass times gravity, force of gravity, is what I chose to be the positive direction. You can choose it however you want, as long as they oppose each other. And this is going to equal mass times acceleration. Do we want to know? No, we just want to know the net force, so we don't actually care about the acceleration. So net force, sum of all forces. Okay. So then, sum of all forces in the Y direction is going to be mass gravity. So mass is 6.14. 6.14 times gravity, which is 9.8, minus F1, which I think was 35 degrees, not 35 newtons, 35 times sine 55 degrees. I'm just going to put a number to that. So we're going to have 6.144, 6.14 times 9.8 minus 35 times sine of 55 degrees. 6.14 times 9.8. Yep, that seems reasonable. And that gives us 31.5 newtons. The x direction up here is going to be 35 times cosine of 55 degrees. And that's going to give us 20.1 newtons. And so what we're going to do here is going to they want the net force. So we're going to treat this as a vector. And so we're going to draw a triangle. And this triangle is going to be 20.1, 31.5, and it's going to be this direction. So to find the magnitude, we're going to do a hypotenuse. So it's going to be 20.1 squared plus 31.5 also squared, and then we'll square root that. So it's just the Pythagorean theorem. Maybe Pythagorean, not entirely sure. 37.4 newtons. And then the angle is going to be tangent of theta equals opposite over adjacent, which is, so I'm going to look for this angle right here. Yep, I'll just call that theta. Opposite 31.5 over 20.1. So solving that, theta equals arctangent of 31.5 over 20.1. Get a value here, arctan of 31.5 divided by 20.1. And that is that 1? That is weird. 1 radian, almost exactly, which is 57.5 degrees. So this then is going to be, so the 2.4, the answer is the vector, the resulting force, the sum of all forces, the net force on the box when net forces on the box, net force on box with F2 removed is equal to 37.4 newtons at 57.5 degrees below the left horizontal. I know, left horizontal feels like a weird way of describing it. It kind of is. What I'm trying to describe by that is left horizontal, that angle right there. So backtrack, recap what we did here. We had a box. We wanted to find the mass of the block. To find the mass, we did the sum of all forces in the y direction. And then we wanted to find the net force acting in the box as F2 was removed. I interpreted that as if we just immediately get rid of F2 without any repositioning yet, which direction does the box swing? What force is net force on it? And to do that, it's no longer in equilibrium, so we just did a triangle, found sum of all forces in the x direction, found all the sum of the forces in the y direction. I guess I should do it vertical for y direction. Did a triangle, found the hypotenuse, and then found the angle using tangent of theta.